Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, well, I'm just going to remind you the 3 books that are on sale. Drink tea and read the paper. If you're a green belt and a black belt and you want simple instruction on how to apply your skill, design of experiments for 21st century engineers, and finally a statistical process control for small batch production. They are all available from lulu.com and the links are in the video below. Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, well, it's part 2 of the case studies that we've been looking at, which is all about process capability improvement. And what you're going to see once again is exactly the same principle being used. Inputs, control the outputs, fix the inputs, and the process capability just comes under control. That's it. It's that simple. I'm a Six Sigma guy. I could teach you maths till I'm blue in the face, but there is no mathematics in this. This is just physics and then damn good process management. Inputs control outputs. Practically fix these inputs and practically you'll deliver great process capability. No mathematics needed, just good management discipline. Let's take a look at another great case study, and at the end of this we'll take a look at all the other case studies, one after the other, that just do this and the process behaves. Let's take a look at the case study. Okay, let's take a look at this case study. Now this case study is all about a labelling machine, and the issue that they've decided to measure as their primary measure is the setup time for this. Now they could have used other measures, but they've decided to use setup time because it's very, very unreliable. You know, sometimes taking up to 2 to 3 hours just to set the machine up correctly. So this lack of consistency, it's just so unreliable. They don't know whether the setup time is going to take 20 minutes or 2 hours, and they're going to use this as the primary measure. So they're trying to get their setup time under control here, and it's not the physical setup so much as the fact that when the machine is set up, it's not reliable. So they have to set it up again and adjust it and adjust it and adjust it until they get the machine to work correctly. So the primary measure is setup time. So there's the problem definition. Here's the measurement. Look, so here's the current performance. So the last 30 batches, you can see the wildness of this process. It's just totally out of control. This is a good example. You know, I say to people, there's 3 states your process will be in. It'll be in a state of chaos, control, or excellence. What does chaos look like? It looks like a graph that does that. This is a process in complete chaos. So there is the current performance. That's the last 30 batches that we're using as a reference. Now what they're also going to do is they're going to keep an eye on the defect rate at the same time, but this isn't their primary measure. This is a secondary measure that they're going to keep an eye on, because nobody's going to thank them for getting the setup time to be 20 minutes, but the machine just produces piles of rubbish, lots of defects. That wouldn't be a good setup reduction project. So we're going to keep an eye on this one as well. And again, you can see it's pretty chaotic. You can't really predict what's going to happen to the defect rate for each of those batches. Now look, what do these guys do? Well, they do what you saw in the previous case study. They go process flow. There's the machine, by the way, labeling the products. Yeah, so it's just, everybody's got one of these. It's just a pretty standard labeling machine, but if you can't get the labels on the products, and by the way, these are drugs, so if you don't get the label on these drugs properly, they can't go out the door. You might have made the product perfectly well, but if you can't label it properly, this is a super important process here. So it's just showing you how the machine works, etc. Now here's your cause and effect. So Just like the previous example, there's very little control here. So they're saying that the applicator speed, the monthly maintenance, and the fixed teams are under control on the applicator pad down here. But you can see the rest of it. Look at the ends. The ends mean that they have no control. These are variables that they have no control over. And there's your problem right there. Highly chaotic result, many variables, and of course many variables create chaos. Let's get rid of the chaos. Let's control them. So they literally just go through this, like the last case study. And here are some of the things they concentrated on. We'll concentrate on the 2, 3, and 4 before we look at training. But blade pressure, blade condition. The conveyor modification was to make something permanent that they sort of cobbled together. So the condition of the modification wasn't particularly good, and they had to keep sort of working on their modification to keep it in good shape. The modification worked, by the way, so they just said, let's do it properly, let's do it permanently. So the conveyor modification and the belt condition. So they were the controls put in place after the first 30 batches. So you can see some things here. The conveyor modification, look, is in this photo, and it's simply a PTFE plate that just reduces the friction as the product travels down here. Previously what they were using was tape, so they were using a temporary solution. It worked, but the tape got in poor condition and they had to keep replacing it. So as it worked, let's make it permanent. So the adjustment of the blade pressure, look, he's even stuck a label over the top of it that they use for products, so that now they know that the blade pressure has not been adjusted. So a nice little mistake proofing device there. The blade pressure, and here's the point, the blade pressure has been fixed, never to be moved again, and that label's going to make sure that that doesn't happen. Then we talk about a little bit of maintenance, cleaning the blades, because of course as a sticky label slides over the application blade, it leaves a little bit of adhesive behind, and eventually that starts to cause problems. So what do they do now? Well, they clean it at the start of every job. Straightforward. They also clean the belt, because again there's a printer that's printing the labels, and the printer leaves ink on the belt. When the ink gets bad enough, when the contamination gets bad enough, the sensor starts to misbehave. So again, we clean the belt now at the start of every job. This is straightforward. I've said this before. Every variable, if you have a variable, single variable, controlling a single variable equals, can't spell it. Controlling a single variable is easy. And that's all you've got to do. Identify the variable and come up with a control. So you can see now there's some more C's now, and they've identified these as green. So there's a few more green C's appearing on the cause and effect diagram. Then what do we get? Well, now you can start to see the process starts to calm down. So we've already, look, we've cut the top. We've cut the top off the chaos. So you can already begin to see the improvement in control with the variables that he's used in the first part of his improvement work. Okay, now the defects, look. The defects, well, there's a little bit of chaos here, and I think he might tell us a little bit more about the peaks. There were a couple of problems there that they had, but the defects, once they get control and they get everything sorted, they begin to get a level of quality which is along with the best that they've seen. And this is the point. Control always equals best. Yeah, so You cannot be consistently poor at something. If you get consistency, you will get best performance. Let's keep going. Now they go on to other things. Real tension, ampule height. So there are glass ampules that are being labelled here, and the height of the ampule is causing a problem. Let's keep going. So you can see the problem with the belt tension. So the tape here that's going around here has sort of gone loose, and that creates a problem. So we have to get the belt tension right. And here's the problem with the ampule height. Look, all of these ampules are different heights. This was never a problem before, but now you're trying to get consistency in the labeling machine. Actually, this part of the process, the sealing part, is really important. So suddenly they're having to put a standard further up the process that's never been needed before. So we need to improve the consistency there, so all the sensors work and things like that. Okay, now you can see some more green C's that have appeared on the cause and effect. So let's take a look now. How are we doing? Well, look at the process. The process now is beginning. It's beginning to just go down. It's beginning to behave itself. Yes, we had a bit of a problem there where we tried to do a component swap, so they're trying to do a little bit of analysis and how the process was behaving. But look at what's happening. Control the inputs and you get control of the outputs. Not a root cause, by the way. So let's be clear about this. This problem, I need to say this a number of times, it has no root cause. There is no 5 whys in solving this problem because there is no root cause. There is just lack of control. Let's take a look at the defect rate. Now look at the defect rate. The defect rate is beginning to behave itself as well. You know, so suddenly that's going nice and consistent, regularly below 0.5%, much more consistent. That's what we're looking for in Six Sigma. What are we looking to do? We're looking to take all of this wild chaos away. That's what Six Sigma's about. People think it's about maths. It's about process control, and there it is in spades. So there's some more things that they've got to do. Settings by eye, code equality, setting up the sensors, etc. So there's more work to be done. So let's have a little look. So they put here, look, they've put some scales on here to help with the settings. So suddenly there's some measurement scales. There's also a bubble controlled level there so that they can set the blade up properly. So we're giving people the tools to get a consistent setup, to always set the machine in the same place. Some of the scales already exist. Let's blow this up. Look, the machine came, whoops, not there, the machine came with these controls in place. So you can see the scales. So there's one here, there's one here. So we do have some controls, we do have some possibility of some really great control. Now unfortunately what they're finding is that the material that comes in is a bit inconsistent, so he's insisted on coming up with ranges for these. Now this is not ultimately where you want to be, that you want no ranges, but he feels he has no choice given that the material that comes in has never been specified correctly, and he has to have the range to deal with the movement in the width of the tape, etc. So there are a few ranges there. Not my preferred way of behaving, but hey, he's beginning to get control. There was nothing here before. No suggested settings, no ranges, nothing. So he's beginning to get control. So the next steps here, he needs to put in place the 5 controls that he stated previously. So where were we? So he needs to put those 5 controls in place. So there's more to be done, and he knows it, and he needs to tighten those up, get the material under control, and then get the ranges tightened up. But what have we seen? Currently The setup time is consistently below 45 minutes, which I think was his target. I don't know whether we've got a run chart. No, we haven't. Let's go back to the run chart. There's his run chart, look. You know, my view is once they get this right, I mean, look at those there, the way that is performing, that's what's going to happen consistently. I mean, that's below 20 minutes, those performances. But as he says, we are regularly below 45 minutes, and I think they're going to get this down probably to 15 to 20 minutes, and of course with a very low defect rate, almost, you know, 0 defects. When they get this thing running properly and they get all the controls in place, I think 0 defects is definitely possible. Once again, another fantastic example. No mathematics in the whole thing. Where were the statistics in that? There are no statistics, because what is Six Sigma about? It's about variation. And what he demonstrated was how to control variation, and if you do that, you improve your process capability. Well, I hope you enjoyed that case study. Again, it's just using this. It's fantastic. You use it, your process behaves itself. Let's remind you of other case studies we've shown you with exactly the same procedure. Process flow, cause and effect. Bring this principle into play, control the variability, improve your process capability. Let's take a look at case study after case study. Okay, here's case study number 1. It's the Royal Mint. This is an annealing process. So let's have a look. Process flow, cause and effect. They identify the variables. They identify things that they're going to control. They go away and they put controls in place for these wild variables. And what happens? Look at that. Look at that yield. Now, let's be clear. This is process capability. It's not the traditional CPK measure, but this is process capability, which of course is pass-fail. And they just drive the capability right to the top of that chart. There's example number 1. Let's look at example number 2. Now we've moved away from an annealing process. It's a packing process. Process flow. Now this packing machine is creating defects. It's breaking down, and because it's food, they're having to put the food in a freezer, and then they're going to have to come back and they're going to have to rework the product that they weren't able to pack correctly right first time. What technique do they use? Process flow. Cause and effect. They identify some variables that are crucial to making the machine work properly. They fix the variables, and look what happens to the rework rate. There's a little period in here in the middle where they decide to speed the machine up, and that creates a little bit of chaos, but they don't back away from this. They revisit their standard operating procedures and they get control. What does control mean? It means removing variability. Another fantastic example. Here's another one. Now this is your traditional CPK calculation. The previous two, of course, were lower the better type performance, yeah. So we were driving the graph either lower the better or higher the better, yeah. So we were just talking about pass-fail results. Now what we're talking about is grinding a dimension. Now we're into real CPK. Look at the original performance of the process. This, I've said before, you're either in chaos or control, and people ask me, how will I know? Plot the graph. You will see it on the graph. That is complete chaos currently. What does he do? Process flow. Cause and effect. Look at the ends that he's got for the variables that he's identified. Lots of chaos in his process. No control. They've implemented this in a chaotic, half-arsed way, and now they have to go back and pick up the mess. And that's what Six Sigma projects often do. They are picking up the mess from a project that hasn't been implemented correctly. Now, once he gets control of the process, now what he seems to be seeing now, look, of course, is a gradual drop off on the dimension. At some point he's probably going to have to regrind and reset, but that process, that's very easy to get to 0 defects right now, and a fantastic CPK transformation, process flow, cause and effect, identify the variables, control the variables, and physics kicks in. And finally, of course, the case study that we looked at in part 1 of process capability improvement case studies. Just a reminder, this is the welding process. We had rework. What did they do? Process flow, cause and effect. They put some controls in place, wrote some standard operating procedures, turned many of those ends, many of those variables that weren't controlled, into controlled variables, and transformed the performance of their process. There's the transformation. Now again, this is a lower the better graph. Still process capability though. They've just driven that result down and they've made the result behave itself. That's what process control is about. Taking variability out of your inputs. Okay, hope you enjoyed the case study and that little reminder of all of those case studies where they've just done this. This is the Six Sigma challenge. Take the Six Sigma challenge. If you want to argue with me about this, take the Six Sigma challenge. Invite me to your company. I will use this simple principle. If this doesn't work, you don't have to pay me. But just a warning, I'm going to turn up and use the laws of physics. This is like force equals mass times acceleration to me. It's one of the laws of physics. Inputs controls outputs. So unless you are about to break the laws of physics, if I turn up, we're fixing your problem. And that's the centerpiece of Six Sigma. Forget all of this statistical stuff. Yes, it's useful now and again. I teach the statistical stuff as well. But what is the statistical stuff for? It's to help me to just deploy that principle in the best possible way. It is not statistics for statistics' sake. It's to deploy the laws of physics and to make your processes make pots and pots of money. Take the Six Sigma challenge or leave some comments below. Be fantastic if you would subscribe. Take the Six Sigma challenge and make pots of money.